What is up, AP Calculus? Today we're looking at 3.4 velocity and other rates of change. We're going to spend 2 days on this just because it's some word problems. I want you guys to get super comfortable with what they're asking and how to find the answers to them. So we're going to spend a little bit extra time on this section, and hopefully it'll be beneficial to you in the long run. So we kind of talked about this last time, just briefly, not in any kind of detail at all. But we said that if we have a function for position, then the derivative of that function would give us the velocity, and the second derivative of the function would give us acceleration. So that's something super huge in calculus and in physics to remember. And they have tons of questions that revolve around this and test your understanding of, do you know that the derivative of the position is the velocity? Do you know the derivative of that is the acceleration? And they try to trick you in many ways, but if you keep in mind that this is how our derivatives and our positions, velocities, and accelerations are related, then you should be okay. All right, so kind of left a space here so we can look at the problems. This one's not necessarily a velocity. It is in a sense, but we're looking at this circle, right? And we're saying, all right, as we increase the radius, how is the area of this circle changing? Which is kind of cool to me, right? Because we can use our calculus to describe how the area of something is changing in relation to one of its parts. All right, so for part A, it says find the rate of change of the area with respect to radius r. So rate of change is very important here, right? So let's say, well, we know that the area is equal to pi r squared. Right, so if we wanted to change, so it's saying find the derivative with respect to the radius of the area. Okay, well, that means that I'm going to find the derivative with respect to the radius of this thing here. Okay, that's not too bad. So because it says with respect to the radius, we're deriving the r squared. So that's going to be 2 pi r. Notice the pi doesn't change because the pi is a constant. It's just like any other number. We're not going to do anything special to it because it's part of the circle formula. But we are going to deal with the r squared. So we know that the derivative of area with respect to the radius is 2 pi r, which is very interesting, right? For the fact that the 2 pi r is the formula for the circumference of a circle. So it's pretty neat, right? The derivative of the area is the circumference. Okay, so this is part A. We found the derivative and we got the rate of change of the area, right? The rate of change is the derivative of the area with respect to the radius. Okay, part B. Let's change colors here. Evaluate the rate of change of A at r equals 5 and r equals 10. All right, so because we're still talking about the rate of change, we're using that. It's not asking us for the area, it's asking us for the rate of change. So we're going to plug in 5 for r. So 2 times pi times 5 is 10 pi. 2 times pi times 10, equals 20 pi. So what that's saying is that at that moment when the radius is 5, right, for the first one, it's changing, its rate of change at that point of the area is 10 pi. And then for the second one, when the radius is 10, the rate of change of the circle's area is 20 pi. So as the radius is getting longer, we're adding way more area to the circle, which makes sense, right? Because a tiny circle has a tiny area with a tiny radius, but if we're adding on with a bigger radius, then it's going to add way more area. And then last one, C is asking if r is measured in inches and A is measured in square inches, what units would be appropriate for the derivative of dr? So it would be well, the area, right, it says is measured in square inches. So if the rate of change would be square inches per second, right? Because it's the rate of change. It's how much is this area changing, and then the bottom is the amount of time. Okay, next one, last example for today, and it's just basically reading this graph. So it says a student walks around in front of a motion detector that records her velocity at 1 second intervals for 36 seconds. She stores the data in her graphing calculator and uses it to generate the time velocity graph shown in 3.25, which is on the left. Describe her motion as a function of time by reading the velocity graph. When is her speed at a maximum? So the important thing to note here is that this is a velocity graph. It's not a position graph, right? So what that means, let's kind of talk about what velocity means. So velocity is 0. That means it's at rest. Velocity positive means we're moving forward, whatever the forward direction is. And when velocity is negative, that means we're moving backward. And I'm not sure how many of you have physics before, but the differentiation between, well, I shouldn't say differentiation because that's a math term. I don't want to mess you guys up. But the difference, maybe I should say, between velocity and speed is velocity implies a direction. Whereas speed, it doesn't matter if you're going 100 miles an hour forward versus 100 miles an hour backwards, it's still 100 miles an hour. All right, so the importance of this velocity graph is, again, anytime it's positive, we're moving forward. Anytime it's negative, we're moving backward. Anytime it's 0 for an amount of time, it's at rest. So let's look here. All in this graph, all in here, it's positive. So this is moving forward. She doesn't really come to rest, right? The transition period between when you're moving forward and backward is this 0 here. So it's not like she stops for a period of time. It just like for that moment that she's transitioning. Okay, all in here is going to be backward. That's not how you spell backward. Backward. Okay, maybe we should change colors here. In this brief area here, she's at rest, right? Rest. And then the very end is moving forward again. So just some practice in reading the velocity graph, and that's going to be super important as we move forward because they might give you the velocity graph and say, all right, then tell me about acceleration. Or they might give you the velocity graph and ask you, okay, well, tell me about the position at any time. And you've got to be able to understand where we are in relation to the position or the acceleration, and use the parts of the graph, like the positivity, if we're above or below, or negativity, to tell us about the acceleration or to tell us about the position. So just getting your feet wet and making sure you understand that this is the graph of velocity. What does that tell us? How is this person moving around? Okay, that's it for today. Really short, but it's kind of like a lot of stuff for you guys to wrap your head around. So I wanted to sink in, want you guys to get some practice at it so you feel confident moving ahead. Good job.